Hi. So looking at chapter 5, where we start getting into the fun part is with calorimetry. So we talk about delta H so far, enthalpy, in fairly abstract concepts. We've looked at charts and tables to calculate the enthalpy of a reaction using the enthalpy of formation. But how can we actually start to measure this in a lab? So one of the prime ways to do this is using something called a calorimeter. Now, calorimeters can be made very simply, or they can get big and fancy and complex. So you can imagine in a school or educational setting, they're going to be pretty simple. One of the classic ways to do this is to nest two different styrofoam cups together and then seal it with a cork lid. Now, there's typically two things you want in there. You want some way to be able to stir the material, and you need a thermometer that goes through in order to measure the temperature of what's going on in the reaction. What we have at our school is very similar, although just slightly different. We do have a styrofoam container to run the reaction in, but it's also got another level of metal on the outside, and it's got a plastic top instead of a cork top. I'm not saying one is better than the other. They're just going to be different looks to these more simplistic calorimeters. So when we're looking at calorimetry, what we really need to know is the heat flow through material. And that's where we get to two different concepts called heat capacity and also specific heat. So the amount of energy required to raise the temperature of a substance by 1 Kelvin, which is the exact same amount as 1 degree Celsius, because remember they're just relative numbers, is going to be known as heat capacity. Here it's saying it's usually given for 1 mole of a substance too. So this is where when you're working with anything with thermodynamics, always look at your constants, always know exactly what the units are that you're looking at. Now, in this table here, what you see is not the heat capacity, but the specific heat of a substance. So these specific heats are the amount of energy required to raise a substance by 1 degree, which is the same, but it's also only 1 gram of that substance. So it is more amount specific. As you can see here, water has a very high heat capacity compared to our metals, right? As you can imagine, if you think about heating up a pot of boiling water on the stove, it takes a lot more energy to actually heat up the water than it does to heat up your pot. Pot gets pretty hot pretty fast, right? As soon as you put that thing over the burner, you don't really want to be touching it with bare hands. The water inside, however, is going to take a lot longer to heat up because it's going to take a lot more energy to get that water hot. This is a very, very good thing for the planet. If water were to heat up a lot faster, imagine what Lake Michigan would look like in the middle of summer. If it heated up with less energy, there's a good chance that by midsummer, the entire Lake Michigan will have evaporated. And then when it starts cooling down, that water's all going to go somewhere. It would be a disaster from day one. So the fact that water has a really high specific heat is good for our lakes and oceans and good for our ocean life and good for the health of this planet. So this is what I was talking about before. Specific heat capacity, also known as heat capacity, is based on the amount. So it is based off of 1 gram of that substance. Now, if you look, if we were to go back, the specific heat of water we say is 4.18. Sometimes you'll see that written as 4.184. You notice that's equivalent to 1 calorie. So while I could say the specific heat of water is 4.184 joules per gram per degree Celsius, I can also say it's 1 calorie per gram per degree Celsius. So when we're looking at calorimetry, all of this comes into play with this main equation here, okay? Q, as a lot of people say, Q equals MCAT, okay? The way people write this C might vary. You might see it with a CS or a capital CS or a couple different ways, but most places tend to have it as lowercase c, and this is going to be the most common way it's written. And because the delta kind of looks like an A, it looks like MCAT, which, if you don't know, is actually SAT on steroids when you're trying to go for medical school admission exams. So that's where that comes from. So Q, we know, is going to be unit of heat. It's going to be joules. Our mass, we measure in grams. I'm going to get to specific heat in a second. Our delta T, typically going to be changed in Celsius, but change in Kelvin also works. Because all you do is you add 273 to convert, delta T in Celsius or Kelvin, the same thing. If you're given Fahrenheit, that you have to make sure to convert over to Celsius. Now, specific heat, joules per gram degrees C. So just to confirm, our units work out beautifully in this equation. Our grams cancel out, our degrees Celsius cancels out, leaving us just with joules on either side. Now, specific heat versus heat capacity. Typically, specific heat is given for a specific compound or specific element because it's very easy to measure for 1 gram of that material. Heat capacity works a little bit better when you have a more complex system, like the heat absorbed by the calorimeter itself. And that's why oftentimes you will see lowercase c written as specific heat, where you have the grams in there. Capital C, there's no grams in this unit. So if you're looking at trying to figure out if something specific heat or heat capacity, pay attention to those units. Those units are going to tell you everything you need to know. So bomb calorimetry is something a little bit fancier and not quite as scary as it probably sounds. But this is where we often run reactions where they need to be very, very isolated, okay? So, or as it kind of sounds like, we're exploding something, right? If we're running a combustion reaction and we're trying to figure out the energy coming off of that, we need a way to measure the energy given off by the reaction, but not have all that energy just go out into the open. So that's when often you'll have sample ignition wires, you'll have a much more contained substance in an environment that is very safe to use. The amounts of material typically run for this are fairly small, but bomb calorimeters, because obviously they're a lot fancier, are going to be much more expensive pieces of equipment, which is why you don't typically see these, honestly, on a high school campus. Okay. I've got 2 different types of problems here to show you how these types of problems work. What is it that we can do with these calorimetry calculations? Okay, first question. 25 grams of water at 90 degrees Celsius was added to 35 grams of water at 15 degrees Celsius. When we mixed them, the final temperature was 44 degrees Celsius. What is the heat capacity of the calorimeter? So to picture this, we have our closed calorimeter. Good practice, always put in the cold water, then we put the hot water in afterwards, and then we wait and see what the final temperature is going to end up to be. Now, to work something like this through, you need to consider that there are 3 different components in here. We have the hot water, the cold water, and the calorimeter. Now, based on the first law of thermodynamics, and because we assume calorimeters are isolated systems, we can say that the heat from the hot water plus the heat from the cold water plus the heat going from the cup is all going to equal 0. Right? There's going to be no net change. Whatever one releases, something else is going to absorb. Now we know for substance that heat, again, is equal to MCAT. So we can say if we have the mass times specific heat times change in temperature of the hot water, add that to the mass times specific heat times change in temperature of the cold water, plus, now cup, do we have a mass for it? No, right? This is going to be a little bit more complex system. Plus, we're looking for heat capacity. So what we can do is adjust this equation to say Q is equal to heat times, heat is equal to heat capacity times delta T, right? Because remember, heat capacity has a unit of joules per degree C. So if I multiply that by temperature, I'll just get my Q, I'll get my heat. So this equation works really well when you know the specific heat of a substance and you know the mass of it. If you don't know the mass of it, heat capacity is our friend. So here, the heat capacity times the delta T of the cup. These problems tend to look big and scary because they're long algebraically, but they're not particularly hard to solve. There are just a lot of parts to it. So for my hot water, I have 25 grams of my hot water, which since it's water, it has a specific heat of 4.184 joules per gram per degree Celsius, times my change in temperature. Now my final temperature was 44 degrees, and my initial temperature was 90. So that's my first part. Second part, cold water. I have 35 grams of cold water times a specific heat of 4.184 joules per gram per degree Celsius times the change in temperature of my cold water. Again, final temperature 44 minus my initial, in this case, 15. Now we are looking to solve for that specific the heat capacity of the cup. So that's going to be our variable times delta T. Now our final temperature was 44, just like everything else was. But for initial temperature, this is why I say the first thing you want to put in is going to be the cold water. And so that way, our initial temperature of the cup is going to equal the initial temperature of that cold water. And that's going to equal 0. Okay, I solved the math. Again, a lot of this ends up being fairly fancy, but when it comes down to it, when you do the calculations, you end up with negative 566.87 plus 29C is going to equal 0. So our heat capacity of this cup is 19.5 joules per degree Celsius. So that's how we'd go about finding the heat capacity of a calorimeter. You typically do it with substances where you know the specific heats, like water, in an easy system where it's easy to find what's going on. Okay, let's now record this number for heat capacity if you haven't already. We're going to use it again in the next problem. So in this one, in the same calorimeter as the previous problem, we've added aluminum to water, and we're trying to figure out estimate what would be the final temperature of that calorimeter. So to do this, we look at it in the same ways we would before. We look at all the different parts that can contribute to heat. So in this case, we've got the heat coming from the aluminum, the heat coming from the water, and the heat coming from the calorimeter, which I'm also going to call the cup. Again, because it's in a calorimeter, it's an isolated system. Total net heat coming off of this is going to be 0. So for the aluminum, we're looking at MC delta T for the aluminum plus MC delta T for the water plus capital C delta T for the cup. So if we start plugging numbers in, the aluminum has a mass of 8.25 grams. Now, specific heat of aluminum isn't listed right here in this problem, but if you were to go back in the video and look at the specific heat table, or reference that table in your textbook, you will see that the specific heat of aluminum is 0.9 joules per gram per degree Celsius. So we're going to plug in 0.9 into the equation here. Now, final temperature, right? If we're solving for final temperature, how can we find a delta T? This is where we really have to keep in mind what is the definition of change in temperature. It is really equal to our final temperature minus the initial temperature. So the initial temperature of the aluminum was 94 degrees. Okay, I'm going to do the same thing for water. I have 100 grams of water. Water, we know, has a specific heat of 4.184 joules per gram per degree Celsius. And we don't know our final temperature, but we know our initial temperature of the water being 23 degrees. Now, this is where we need the information from the last problem. If we know the heat capacity of the cup, again, which is 19.5 joules per degree Celsius, we can multiply that out. I'm sorry, not by 19, by our initial temperature here. Initial temperature is going to be 23, again, same as the water. And here we go for 0. So again, we have heat capacity times our delta T. Okay, once again, this is probably scarier than it looks. It's just a big, giant algebraic problem. So if I were to do the math, I'm going to get, if I start distributing things out, 7.425 T minus 697.95 plus 418.47. I'm sorry, 0.4 T. Couldn't read my writing there. Minus 9,623.2 plus 19.5 T minus 448.5 equals 0. Crazy math, right? But all we're doing is distributing. All right, let's combine our terms here. So 445.325 T minus 10,769.65 is going to equal 0. Finally, to solve for our temperature, it's going to be 24.2 degrees Celsius. Okay, let's check, does that make sense? So we put something hot at 94 degrees and something cold at 23 degrees. So really, really good sign that our answer is somewhere between 23 and 94. And in reality, we have a lot of water, a small amount of aluminum, and again, aluminum has a very small specific heat. So as a result, we're not going to see a massive heat transfer coming off the aluminum, but it is enough to raise the temperature of that water by just over a degree. Now, the same process can be used in the lab if you're trying to find the specific heat of an unknown compound. So in that case, you would actually have your unknown metal at a set temperature, and you'd be able to measure both your initial and final temperatures. And if you were to solve for the specific heat of that metal, it would give you pretty good information about that would help you identify what the metal actually is. All right, that's a lot of information. I hope you guys are having a good understanding of specific heat, heat capacity, and calorimetry. Let me know what questions you have. Thanks for watching.